welcome to Tal Tutorials. Today we'll be discussing the third chapter of class 10 physics ICSE, and that is machine. So basically what is machine we'll be discussing. See, in our common experience it is easier to open a nut by use of wrench than to open it hand, or you can say it is difficult to pull up a bucket. It is difficult to pull up a bucket with a normal hand, and instead when we are using pulley it is more easier to work through it. So basically what is a machine? See, machine is a device by which we can either overcome a large resistive force at some point by applying a small force in a desired direction, or by which we can gain in speed. Here we meant to see we are doing a larger work, a large amount of work, and we are putting a very small force. This is actually a machine. So what is an ideal machine? See, a machine whose parts are weightless, who is frictionless, and there is no change of energy in any manner, that is an ideal machine. The work output is equal to work input, and the efficiency will be giving, that will be 100%. If you believe me, no machine can be an ideal machine, because no machine can be weightless. There is always the friction of air. So ideal machine is only that we can assume. We cannot say that ideal machine exists in this world. Now we'll come to the next topic, that is four ways in which machines are very useful to us. First is lifting a heavy load by applying a less effort. The best example will be given. A jack is used to lift a car. Second is changing the point of application of effort to a convenient point, or we can say convenient direction. That is third example. Sorry, convenient point that we have given. That is, the rear wheel of a cycle is rotated by applying the effort on the pedal. So we are applying on a pedal and a point, and we are getting a good speed to gain speed. Third is changing the direction of effort to convenient direction. See, if a bucket full of water is lifted up from a well without the use of the pulley, lot of effort has to be applied upward. By using a single fixed pulley, it becomes easy to lift the bucket from the well by applying effort in the downward direction instead of applying upward. Thus, the person lifting the bucket up may also use his own weight as an effort. And the last is for obtaining gain in speed. When a pair of scissors is used to cut a cloth, its blade moves longer on a cloth, which its handle move a little. So this is changing again in speed. These are the four examples, or we can say four functions of simple machine which are helping us in our normal life. Now we'll come to the next topic, that is very important related to this chapter. That is technical term of a machine. First is load. See, load is what? The resisting or opposing force to be overcome by a machine. This is a very simple thing. I'll tell you an example. We have to help a weight of 500 grams or kg, you can anything you can say, to move up. So the 500 kg, that thing is a load here. And then the second is effort, the force applied on the machine to overcome the load. This is whatever we are putting the effort, a muscular force, and whatever things we are using to put that effort to move that load, that is an example of effort. Now we'll come to some technical term which I don't think you will be very aware of. Third is mechanical advantage. This is nothing, it is just the ratio of the load to the effort. So when load and effort are used, they are two similar quantities. So mechanical advantage will never have any unit. Now we'll come to velocity ratio. The ratio of the velocity of effort to the velocity of load and the effort respectively, that is known as velocity ratio, they also don't have any unit. See, I'll explain you. If dl and de are distance moved in the same time by the load and effort respectively, so we are putting dl by distance of load and de is equal to distance of effort. As you can see in your book what I am explaining in the page number 49 of machine velocity ratio, wherever it has been explained. So velocity of load, that is VL. So velocity is distance by time. Therefore it becomes dl by t. And same for effort, velocity of effort, that is distance by time, de by dt. Velocity ratio, as I have already explained you, what is velocity ratio? Velocity of effort by velocity of load. Where I know de by t and dl by t get cancelled. So velocity ratio is equal to de by dl. Thus the velocity ratio is also defined as the ratio of displacement of effort to the displacement of load. Now, before going to efficiency, I wanted to make sure that you know two things, that is work input and work output. What is work input? The work done on the machine by the effort is known as work input. And what is work output? The work done by the machine on load is work output. See, the work output is equal to work done on the load. Now we'll come to the last term which I have shown in this page, that is efficiency, and that n type of sign is nothing, that is eta. Okay. So what is efficiency? Efficiency is denoted by the symbol known as eta, which is shown like n, and efficiency is nothing, it is just the ratio of the work done by the machine to the work done on the machine, that is work output by work input. This is also have no unit because both are having similar quantities. I am sure that you are very much understood now. Now, before going into the next topic, I wanted to have some discussion of ideal and actual machine. See, an ideal machine, I have already explained the first part, that it is that in which no loss of energy is there. Whatever work we are inputting, we are getting the same work output, which is impossible at this point of time. But actual machine is the machine that output energy is always less than the input energy, because there is always some loss of energy due to friction, due to air, anything like that. Now we'll come to one very important derivation. What is this? Sorry. See, we'll come to very important derivation, that is relationship between mechanical advantage velocity ratio and the efficiency of a machine. See here, I am letting a machine overcome a load L by the application of effort E. Let the displacement of the effort be dE and the displacement of the load be dL in time t. So we already know work input is equal to, work means what? Force into displacement. The work input, that is we are putting effort. The work input is equal to effort into displacement of effort, that is E into dE, and work output is load into displacement of load, that is L into dL. So efficiency, that is eta, is equal to work output by work input, as we already know. So L into dL by E into dE, where L by E into dL by dE. We can write like that also, where L by E we know that is mechanical advantage, and dE by dL we know that is velocity ratio. So mechanical advantage also can be written as efficiency also can be written as mechanical advantage by velocity ratio. So mechanical advantage is equal to velocity ratio into efficiency. Hence, the mechanical advantage of a machine is equal to the product of its efficiency and velocity ratio. Now we'll come to the next topic, that is lever. What is basically a lever? See, a lever is a rigid, straight or bent bar which is capable of turning about its fixed axis. This is same principle which we are using on moment or couple, that it works on the principle of a moment. For an ideal lever, it is assumed that rod is weightless and there is no friction at the fulcrum. In the equilibrium position of the lever, moment of the load about the fulcrum and moment of effort about the fulcrum will always be equal. Now, what are the three types of your three classes of lever? There is three class 1, class 2, class 3. Now, before going into this topic, I am telling you just learn this word flea, where F is in between for first class, L is in between for the second class, and E is in between for the third class. That's why flea is very important. So class 1 lever, in this type of lever, the fulcrum is in between the effort and the load. Examples are given there as claw hammer, beam of physical balance, crowbar, seesaw. Class 2 lever, in this type of lever, the load L is in between the effort and the fulcrum. Now again I am telling you what is the example: a wheelbarrow, a paper cutter, a door, a nut cracker. And the third example, the class 3 lever, is in this type of lever the effort is between fulcrum and load. Thus the effort arm is always smaller than the load arm. For example, knife, we have seen that effort is always smaller, load arm is a larger one. Now we'll come to how levers are working in our human body. See, the examples of each class of lever in a human body are as follows. First, the action of nodding of head like this is a class 1 lever. Here the spine acts as a fulcrum, load is in front part, that is this, and effort we are putting from our neck, that is rear part. So this is an example for the first class lever. Second, raising the weight of the body on toe is class 2 lever. Like I'll see class 2 lever. How? If we are walking like this, so that point of time the fulcrum is at the toe and the load is in the middle and effort by muscles are at the other end. And third example is raising a load by forearm like this. When we are raising it, here the elbow joint acts as a fulcrum, bicep, effort, and the load is in the palm. This is the end of this PPT class. In the next PPT, we will be discussing about pulley. So bye bye class, good night till we meet again.